And our next speaker is Vianney Lebouteiller. Thank you.
Thank you. So in this talk, I will present some recent progresses about the methodology and the applications of so-called topological models to recover variations of physical conditions in galaxies. In fact, it's going to be a summary of some results, and it's a first phase within a longer-term project, which is going to continue with the project called Spection, which is co-funded by the ANR and the Swiss National Fund, with the main collaborators on the bottom right. So the main motivations are to interpret integrated galaxy spectra and to account and capture non-uniform physical conditions in galaxies. And as an illustration of that, for instance, it's been quite a few years now that ALMA and more recently JWST have revealed in their high redshift galaxy spectra the same diversity and complexity of the ISM and energetic sources that you observe in nearby galaxies, which is not surprising, obviously. For instance, just with ALMA for single galaxies, you can detect C2 and O3, and with just 2 lines, you have a multi-phase ISM that you have to account for. Also, restrained optical emission lines like O3 and O2 reveal some kind of non-uniform physical conditions. And all of that just reflects expected variations that you have in galaxies. For instance, the density probability density function, H2 region luminosity functions, etc. What these observations also reveal, and this is shown here, it's part of the JD sample between redshift 5.5 and about 10. These are optical emission lines observed with JWST. What these observations reveal are extreme ISM conditions, globally low metallicity and extreme ionization parameters, which you can kind of see in these BPT plots, famous BPT plots, which compare 2 line ratios versus each other and compare to photonization models. And the question becomes, this kind of diagnostics with 2 line ratios calibrated on single 1D models, are they able to capture the diversity that you expect in these galaxies? And what is the meaning of quantities that you get, for instance, metallicity or density using such models? Do they represent some kind of averages? Another way to think of it is if you have a galaxy that looks very simple because it's just a dot, but probably it looks like something like that, is it okay to model it using a very simple model? And in fact, in the high redshift community, this question has been going on for some time because they have to invoke such, more complex models to match the observations. And their approaches is often inspired by the approaches used in nearby galaxies. Nearby galaxies provide the opportunity to give access to many bright tracers, but also we have the chance in the nearby universe to have a wide range of parameters in galaxies, including very low metallicity or even extreme objects. We can also, with nearby galaxies, study them with IFU data, which makes it possible to benchmark the recovery of internal variations. And on the right, I show 2 examples of high redshift studies that invoked multi-component models, for instance, with the covering factor of the photodissociation regions, or 2 components with different electron temperatures or electron densities. And these were needed to match the observations. But in general, the motivations are much broader because basically at any redshift, spectroscopic tracers will always represent a mixture of physical components, maybe because it's spatially unresolved because you have a faraway object, a high redshift galaxy, or a compact object at low redshift, like a dwarf galaxy, or something intermediate like green pea galaxies, or observations like in the far infrared where you don't resolve the components. In general, you will also mix the different ISM phases, and even if you have IFU data along a single line of sight toward a single pixel, it will be a mixture of physical conditions also. And it is important because some specific quantities will be particularly sensitive to the exact mixture properties. It can be the density, the escape fraction of ionizing photons, which I will talk about, or the molecular gas mass fraction, the molecular gas filling factor, sorry. So the goal is to interpret multi-component spectra. We want to account for the complexity in the modeling. And if we can account for it, then it means we can recover that complexity in order to interpret it physically. So in a way, another way to say it is try to do IFU science without IFU data. And for that, we're guided by expected variations and distributions. Some of them are known theoretically or drawn from observations about the density, the luminosity, the matter boundedness of H2 regions, metallicity gradients, etc. So these are all things that we expect. And you have different approaches to account for that complexity, from 1D models to 3D models. 1D models are state-of-the-art radiation transfer models and state-of-the-art chemistry. 3D models are very good for the geometry, but geometry is not a free parameter per se. You have to force it. You can use simulations, which are able more and more to capture the diversity of the ISM physical conditions and the diversity of the sources, but they are expensive in resources. And globally, there is not a perfect approach. The choice is merely driven by the science goal. And to illustrate that, there are some simple scaling relationships, for instance, to get the star formation rate or the ionized gas mass that are perfectly okay with single 1D models. But what I will present is more of a data-driven approach to tackle topologically dependent science questions. And for that, we will combine 1D models to describe the sum of the emission of emissive components of a galaxy. So combination of 1D models, the microphysics will be encoded in the 1D models, and the combination, you can think of it as a phenomenological approach. It is not a spatial decomposition method, and I will come back to that. On the top right, you have the most simple topological model you can think of, which is n times the same 1D model. But of course, you can do more complicated things. You can use a statistical distribution for the density, assuming a normal distribution or a broken normal double normal distribution or whatever you want, inspired by the theoretical prescriptions, for instance. So these are some examples. So here it's, sorry if it's not, the contrast is not very good. So that could represent a galaxy with many emissive components, and you can choose a single density, ionization parameter, metallicity, or age, and that will be distributed among all these components. Or you can do something more complicated. You could think of a power law distribution with some boundaries, or a normal distribution with some boundaries, while some parameters remain as a single value. And it will produce some kind of distribution that could be seen as more realistic. So to make more topological models, you need a large database of 1D models to draw from, and you need a statistical framework for the inference and the predictions. An important caveat is that the combination of 1D models will be done a posteriori, which means that the components are physically independent. And that's why it's called topological, because the different mixtures with the same weights will provide identical predictions. Here it's an example of a combination. You have a linear combination with different weights. The weights will be inferred by the statistical framework. And here we will combine different 1D models with different depth. The clad depth is a free parameter. It's going to follow a statistical distribution. The 1D models themselves are different. You see the electron temperature profile is not the same. And we will combine them in order to make a galaxy with different emissive components. Or you can think of it as a single stellar cluster with different ISM sectors around it. Topologically, it's actually the same thing. Yeah, so that's, I want to say also that it's a very fast-changing landscape with many tools that become available, and also with the technical capabilities, with machine learning and GPU. What we've done is to develop that code that Liz mentioned called MULTIGRIS. It's agnostic to the grid use, so you can plug in any 1D model grid database that you want. But of course, we made it work for ISM models in particular. ISM models which are known to have many free parameters and multiple degenerate solutions. And that's why we used a couple of tools, packages that enable, in particular, this sampling method, which is called sequential Monte Carlo, which is a type of particle evolution technique with independent metropolis Hastings kernels. And so the way it works is that you sample the prior space with various samples. It can be thousands, tens of thousands of particles, and each particle will evolve through its own independent metropolis Hastings chain. There will be important sampling also calculated, with some samples being left out or reappearing in some higher likelihood regions. And eventually you will converge to, well, hopefully, to the posterior distribution. And this is an illustration of so this SMC sampler versus a typical walker. So in the SMC sampler, you start with the entire prior space. Here, it's only 2 parameters just to illustrate. I thought I uploaded a new version. I guess I didn't copy the file. It's okay. So you sample the entire prior space, and then slowly, the particles will converge to the right location. So you have to imagine that. And the typical walker will jump from one solution to the other when you have several solutions. So it's very powerful. So the inference with this code is on the fly that enables to have nuisance variables such as the mixing weight and the distribution hyperparameters, of course, but also other things like the extinction screen parameter. It's meant to deal with millions of 1D models, and it has a GPU layer, and some proofs of concepts are underway, like hierarchical approach and simulation-based inference. I will go fast on that, but these models can be seen as very complex when sometimes you have only 1 or 2 lines to work with, especially at high redshift. So is this really an issue? We use 2 premises. First, a galaxy remains the same with the observation when the observations differ. That means when you have 50 lines, 2, 1, or even 0 lines available, the galaxy is the same. And then the parametric model that you use to describe a galaxy describes its physical structure and conditions. So the conclusion is that the underlying model that we want to use should remain as stable as possible against the different observations. And it means only the predictive power will vary in precision, becoming more and more precise as observations become more and more informative. I'll go fast, but I just want to say that point, it's important for me. Some systems are really irreducibly high dimensional, and if you force a parsimony, it will destroy their structure. So that means that it's not because a simple model fits well 2 or 3 lines, then that the model predictions will be okay when more lines are available. Now, in the few minutes I have left, I'm going to present some applications, some results, and it's basically revisiting some astrophysical questions, adding the topological parameters to the inferred parameters and the interpreted physics. And I'm going to start with the escape fraction of ionizing photons, which is an important quantity and related to the cosmic ray ionization. We want to understand how that works. The direct measurement of the Lyman continuum are difficult at high redshift because of the absorption by the intergalactic medium, and the measurements are line of sight specific. And JWST has made a lot of progress, and we are able now, and with plenty of different observations, ancillary observations, there are multi-parametric analyses that are really powerful in their predictions, but the physical reasons behind a low or high escape fractions are still unclear. What's clear is that the escape fraction will depend on the matter boundedness of the H2 regions. It needs some low density channels to escape. So it is a topology sensitive, topology related quantity. So Liz, in 2022, inferred the escape fraction from emission lines in the dwarf galaxy survey. It's a global quantity. It's not a line of sight specific quantity. So the comparison should be done very carefully. If it can be done, because for most galaxies, we don't have the direct quantity. Anyway, the result is that the escape fraction in star-forming dwarf galaxies on average is higher at in low metallicity objects, and pretty low at solar metallicity also. There is a wide dispersion here, which we think is related to a feedback effect. So it's not just a metallicity effect. The values can seem high, and there are plenty of caveats, and I can talk about it if you want. But for instance, this galaxy is known, well, it's suspected to be a leaker, even though the continuum couldn't be observed, and it has a pretty high value in our inference, so it's pretty reassuring. And inversely, another galaxy has escape fraction measured, which is very low, and we do infer a low value, so all of that is pretty reassuring. The next part is going to be to calibrate this method on a sample of known leakers with direct Lyman continuum measurements, because we have more and more of these sources, and it's the postdoc of Mariam Ediati in the Spection project. And of course, in the future, there will be HWO with direct far UV measurements for individual lines of sight within nearby galaxies. It's going to be very powerful. And the second thing I wanted to mention is the energetics of the neutral star-forming gas reservoir. The question here is what internal feedback mechanisms hit and regulate the star formation process over cosmic timescales. The main star-forming gas reservoir in galaxies is the neutral atomic gas, and in Milky Way-like conditions for solar-like metallicities, the heating of that gas is going to be dominated by the photoelectric effect on the pHs and very small dust grains, and the cooling will be dominated by C2 and O1. However, when you reach extremely metal-poor galaxies, then several things start to happen. The dust-to-gas mass ratio drops, the pH abundance drops, and at the same time, you have a higher abundance of X-ray binaries at low metallicity, which is known observationally and actually expected theoretically as well. And so these two effects conspire to reduce the photoelectric effect heating and also increase the X-ray photoionization in the neutral gas. At the same time, theoretically, so this is the paper of Vianney and Sternberg, you expect some kind of transition between the photoelectric effect heating and the cosmic ray heating around 10th solar metallicity. But here the X-ray photoionization is not included. So this is where we stood. And then Maxime Varese published a paper last year using a MULTIGRIS and the 1D model database, where he showed that the photoelectric effect heating becomes subdominant below 1/10 solar metallicity. So this is the panel here. And the photoionization and the cosmic rays seem to compensate at low metallicity. Even though we don't know what the nature of the X-ray source is here, this is an important finding. And we were able to update it using a wider sample and a new database with a completely revisited X-ray binary prescription and cosmic ray prescription. And the result still holds. The metallicity threshold seems to differ a little bit. It's more like 1/5 solar metallicity now, where the photoelectric effect becomes subdominant, and the cosmic rays seem to drop drastically in these new models, with the photoionization by X-rays becoming quite important. And I guess I don't have time to talk about that, but we also tackled the mass-metallicity relationship in a large sample of galaxies to infer a robust metallicity measurement using strong lines and find consistent measurements, measurements that are consistent with the direct TE measurements that use auroral lines that are much more robust, but it shows that we can recover that kind of robustness without these faint lines. And I will finish with this slide, which is just a summary. We are going to do more with the X-ray binaries and the shocks. That will be, it's the PhD project of Georgina Samson-Olalde, distinguishing between X-ray binaries and AGA, intermediate mass black holes. That's the project of Dhrubajyoti Sengupta. And method-wise, we would like to calibrate all these methods using simulations, but also IFU data, which we have started to do, and possibly a single star-forming regions in Milky Way and Magellanic Clouds to do a scale analysis. Thank you.
Thank you. Due to time constraints, we have time for 2 quick questions. No questions? Do we have something on Zoom? No. I have a very quick one. You mentioned, so you mentioned cosmic ray ionization. Can you relate that somehow to the ionization fraction? Have you looked into, is it even possible to connect these two in terms of your work?
Well, both the X-rays and the cosmic rays will result in the neutral gas being partially ionized, yes. For the X-rays, it depends on their energy. So it depends on the nature of the X-ray source you would include. But yes, I didn't show it, and actually I'm not even sure we did a PDF of that, but we have the ionization fraction of the neutral gas. I can't tell you on top of my head how much it is, but I'm sure it reaches 1% easily with the kind of sources we have.